In this video, we are going to be looking at one of the methods to write the rate law for a reaction. And the method that we're going to be doing is often called the method of initial rates, or what I have referred to it as just method 2. So in method 2, what you're given is you're given a series of experiments. So in this problem here, you have a series of experiments, and the reaction contains 3 components. And so the 3 components are H2SeO3, and then hydrogen ions and iodide ions. And they react together to make iodine, selenium, and water. So here we have the balanced reaction. So for a rate law, it is how the reactants react at a certain pace that leads to a certain rate for a reaction. So with this method, to begin to figure out what this rate law is, what you want to do is you want to write the generic rate law for this reaction. And that rate law is going to include all of the reactants. And so a rate law, you always begin with writing rate equals, and then the rate constant, K, and then your first reactant, which is H2SeO3, and then raised to it, whatever order, and you don't know what the order is, so I'm just going to put an M. And then the next chemical is the acidic hydrogen ion, so that's H+. So you got your H positive, and we don't know its order, so I'm going to put an N. And then the last reactant is iodide. And I'm going to put a P. And I'm not going to put an O because an O looks like a 0. And so I don't want to get confusing, have it look like a 0 when it's an unknown letter. And so our goal to get this rate law is to figure out what the order for H2SeO3 is, what the order of the hydrogen ions are, and what the order of the iodide ions are. To do this, you're going to choose one of the chemicals in the rate law. So I'm just going to start with the H2Se. And so with the H2Se, what you want to do is you want to find 2 experiments where its concentration changes and the other chemicals do not. So if you take a look, experiments 1 and 2, the H2SeO3 increases by a factor of 2, and the hydrogen ions don't change, and the iodide ions don't change. So we could use experiments 1 and 2. And you could also use experiments 1 and 3, but you couldn't use 4 and 5 because both 4 and 5, the hydrogen and the iodide both change. So I'm just going to choose 1 and 2, but like I said, you could use 1 and 3 also. And so to figure out, I'm just going to do H2SeO3. So that's going to be my focus. So I'm going to do the larger of the experiments first. So my larger data would be experiment 2 because 0.020 is a higher concentration. And so I'm going to do the data for experiment 2 on top over experiment 1 data. And so you just plug the data into the rate law. And so the rate law is rate. And so experiment 2 rate is 3.30 times 10 to the negative 5. And then you do the other side. You don't know what K is. We know that the H2SeO3 is 0.020 molar to the M. The hydrogen ion, 0.020 molar to the N. and iodide 0.02 molar to the P. And then directly under it, you plug in the data from experiment 1. So the rate of experiment 1 is 1.65 times 10 to the negative 5. And then you have rate constant. And the concentration of H2SeO3 is 0.010 molar to the M. Hydrogen is 0.020 molar to the N, and iodide 0.02 molar to the P. So all my data is plugged into the rate laws. So now you can simplify. And you can only simplify like things. So on this side, rates are alike. So you can divide those two. So when you divide these two numbers, you get 2. On the other side, you have a K on top and a K on the bottom. They are identical, therefore they cancel. You also have a 0.020 molar to the N and a 0.02 molar to the N. So they are identical. So they cancel. And a 0.02 molar to the P on top and bottom. So they cancel. And so the reason that you kept the hydrogen and iodide constant is so that you cancel them. So they're canceled. So on the other side, the only thing we have is the concentration of the H2SeO3 raised to the M power. And so since they're both raised to the M, we can divide the numbers. And when you divide these two numbers, you get 2. So that's 2 to the M. And so 2 raised to what power is equal to 2? Well, 2 raised to the first power is equal to 2. And so the order for the H2SeO3 is a 1. So I'm going to go up here and I'm going to cross out that M and I'm going to put a 1 in its place just so I know that I've already figured it out. And then we're going to repeat the same thing and we're going to find 2 reactions where hydrogen changes and the other 2 chemicals stay the same. And so if we look at the first column, 1, 4, and 5 leave this first chemical constant. 1 and 5, hydrogen's constant, so I need to choose 1 and 4. And we do the bigger numbers on top, so that's experiment 4. So we're going to do experiment 4 over experiment 1. So experiment 4 values, we have 6.60 times 10 to the negative 5 over 1.65 times 10 to the negative 5. And then we plug our data in. Experiment 4 experiment 4 for the hydrogen and for the iodide. And then experiment 1 for each of the chemicals. So we can cross out things that are identical on top and bottom. So the 0.020 to the P is on top and bottom. The K is on top and bottom. And the concentration of H2SeO3 is on top and bottom that are identical. So when you divide the 6.60 times 10 to the negative 4, you divide it by the 1.65 times 10 to the negative 5, you get 4. And then when you divide these two, you get 2 raised to the n power. So 2 raised to what power will give us a 4? Well, that would be 2 squared. And so our order for the hydrogen ions is a 2. In our last one, we also have to figure out the order of the iodide. So we need to choose 2 experiments where iodide changes and the others stay the same. And that will be experiment 1 and 5. Iodide doubles, hydrogen stays the same, and the acid stays the same. And so the bigger numbers are in experiment 5. So all the bigger values go on top, smaller values go on the bottom. So 1.32 times 10 to the negative 4 K, and then concentration of your acid, concentration of the hydrogen ions, concentration of the iodide. We don't know its order. On the bottom, the data for experiment 1, 1.65 times 10 to the negative 5 K, the acid concentration, the hydrogen ion concentration, and your iodide concentration. So we cross out common things. We cross out K. We cross out the acid concentration, the hydrogen ion concentration. When you divide the iodide, you get 2 raised to the P. Okay. When you divide the rates, you get 8. So 2 raised to what power is 8? That would be 2 cubed. So it's not 2 times what, it's 2 raised to what. So the order would be 3. So this order is 3. So if we take each of these and we rewrite it, then we get rate equals K times the H2SeO3 to the first power, hydrogen ions to the second power, and iodide ions to the third. That was first order, second order, and third order. The overall order would be the sum of each of those. 1 plus 2 plus 3, which would be the 6th order. So now we know what the orders are for each, but we also need to know what the rate constant is, because this is a math equation. And so at this temperature, this rate constant is constant. And so we need to know what it is so we can actually use this math formula. So what you do is you plug in the data from the experiments into the rate law and you solve for K. So if we do this, I'll just use my calculator I have here. If we plug it in to the first one, then we will have a rate of 1.65 exponent -5, and we are going to divide it by, it's case by itself, so we got to divide by each of these. We divide it by the concentration of H2 to the first power. So we had 1.65 exponent -5 divided by 0.01, the first power. We're going to divide it by 0.02 squared, and we're going to divide it by 0.02 cubed. Equals. So our rate constant is 515,625. If we check with another of the rates, so let's just choose experiment number 4. We plug the rate in here, 6.60 exponent -5, and we're going to divide it by the concentration of your acid, 0.01 to the first power, divided by hydrogen ions squared, divided by iodide ions cubed, equals. Okay, there we have a different number. And so let's double check the math. So we have 6.6 exponent -5 divided by 0.01 to the first, 0.02 squared divided by 0.02 cubed equals, okay, I plugged in the wrong number. So it is 515,625. That is our rate constant. But what you need to do is, because it is easy to overlook certain numbers, and it's also easy to accidentally choose the wrong exponents, you want to go through and you check the rate constant for at least 2 or 3 of these, because if the rate constants don't match up, then you've made a mistake either in the calculation of the rate constant or in the determination of the order.